Hey guys, so another video. So for those of you who don't know me or new to the channel, my name is Oscar Savalainen. I do a lot of AI stuff and in particular a lot of neural network quantization stuff because that's something I have a specialty in. And today's video is going to be on quantization aware training, but first I'll do a little bit of housekeeping. I do have like a new microphone and a camera on the way. I know the quality has been garbage. It will hopefully not be garbage going forward in the future, but I still wanted to get this video out just because people have actually messaged me and they've been like, hey, could you do something on like this topic and this other topic? So this is one of those topics, quantization aware training. And yeah, so I'm going to be doing it on this and general kind of theoretical knowledge first on quantization aware training. When you quantize a model, the general process is you take a floating point model, you train it up to a certain level when you're happy with its performance, and then you quantize it. And when you quantize it, there's two broad categories of techniques that can be used. There's post-training quantization, PTQ, and quantization aware training, QAT. And these differ basically in how they approach the problem, and often you'll use both. You'll do PTQ, then you'll do QAT. But PTQ used to be fairly simple. Like in PyTorch, the way they do PTQ and the way they supported it is that you literally just have your model, you quantize it, and then you feed calibration data through the model. And then each layer is individually responsible for finding quantization parameters that are going to work well for that layer. And to find those quantization parameters, you can use many different kinds of heuristics. Like a very common one is mean squared error. So let's say you're feeding data through the model and you have some arbitrary layer in the middle of your model. What that could do is that it could see the floating point tensor coming in and it could quantize it. And it could try to find quantization parameters so as to minimize the mean squared error between the kind of floating point output and the quantized output. So it tries to make the quantized output as close as possible according to the mean squared error as it can to the floating point tensor, and that's kind of a way to find good, quantization parameters. That's a common heuristic, but there's a million heuristics. You can try to minimize clamping, you could try to minimize KL divergence, you can do anything. Like you can be super creative and make your own, whatever you feel. And that's what I would refer to as kind of classic PTQ, but like I said, the PTQ keeps growing as a family. It used to be simple and now it's getting more and more complex. And there's a bunch of different techniques like cross-layer equalization, bias correction, smooth quant, add around, and then specifically for like linear layers and specifically for like transformers, AWQ and GPTQ. There's a bunch of different quantization techniques. There's a lot of stuff that you can try to make your quantization good. But yeah, those all kind of live under the category of post-training quantization, but quantization aware training is kind of a different category of solution, and it's pretty simple. If you know the concepts of training a floating point model from scratch, then this won't seem super shocking to you. You basically have your quantization parameters, you treat them as parameters of your model, you put them into the optimizer, and then you just do a training loop. You just have the model train in quantized space. So again, like when the floating point tensor comes to like a quantized layer, it's going to get quantized, it's going to have a quantized output. It will live in fake quant space, so it'll still technically be a floating point tensor, but it'll always get snapped onto that quantization grid. And then that's just what the model sees. Like you're a layer somewhere in the middle of the model, you're going to receive a kind of fake quant tensor, you're going to do your operations, you're going to pass that forward, again, producing a fake quant tensor of your own. If you're loading a weight tensor, you're going to perform a quantization operation on that to deal with like a fake quant weight tensor. And yeah, that's the basics of QAT as far as the forward pass is concerned. There is a bit of a subtlety in the backwards pass, which is that the rounding operation in the quantization operation is not differentiable. And so you need to, typically people use something called the straight through estimator, which basically means you just ignore the rounding operation when you backpropagate your gradients. You're just like, I don't want to deal with this, just ignore it, and it works. But then there are more kind of advanced versions on the straight through estimator, which include things like LSQ, like learned step size quantization. But anyway, that's not relevant for really today's video. That's kind of a more theory thing. I'll probably have a video on that in the future. But yeah, that's the basics of it, right? Like we put the quantization parameters into the optimizer, we train the model in its entirety, the quantized model, we train it in quantized space, and then the hope is that the optimizer, the gradients, they're going to be smart enough to figure out how to optimize this thing for us. So that is the basics of QAT. And that's what we're going to be doing a coding tutorial on today. We're going to take our FX graph mode quantized model, our ResNet 18 model that we've been dealing with in all of these tutorials, and we're going to do a little QAT training loop, and yeah, we're going to see how that works. So let's get into it. Okay, so onto coding. So if you've seen my previous tutorials, you'll probably be familiar with the setup. We're dealing with a ResNet 18 model, but in particular this code is built off of the FX graph mode quantization tutorial. I would recommend you check out that. It was a series of 3 videos. I would particularly recommend probably the first video just to get the basics, but the second video is kind of more advanced things to do with QAT, and the third video is like advanced graph manipulation and traversal. You don't need to see all 3 videos. The first one will give you the basic gist if you haven't seen FX graph mode quantization before, but that is what we're dealing with today. So I'm going to assume you have seen those videos, and I'll just kind of talk about what the differences are in today's code versus in those tutorials. So you'll be familiar with this evaluate folder as well. This is just how we're going to evaluate our model. The only real differences is that I've generalized it, whereas previously we were only dealing with a specific image of a dog, and specifically we were dealing with this picture of this little handsome man, the Samoyed. This was just hard-coded into our evaluate function. When we were evaluating how well we did our quantization, we were always just judging how well the model could classify this as a Samoyed. But I've now generalized it to basically work with any of the ImageNet classes, because the ResNet model torch vision publicly available weights were trained on the ImageNet classes. Specifically, they were trained on 2012 ImageNet competition data. That data is publicly available. I'll put the link in the description, but I'm not actually using that dataset because it was like 128 gigabytes to download onto my computer, and I was like, there's no way I'm doing that. So what I've done instead is that I've downloaded a bunch of images just from Google Images. Like, these are clogs, like Dutch clogs. This is a hen, this is a very blurry image of a mailbox, and then this is a Samoyed. The key thing is that each one of these images is named the same as they are in the ImageNet classes. Like, if we search for clog, that comes up. If we search for Samoyed, that comes up. If we search for hen, yeah. So the names of the images exactly match the ImageNet classes, and that's kind of necessary to make this evaluate function work. This is not the best code known to mankind. This could be generalized. These could be given like some sort of like metadata that said this was a hen, this was a clog, or whatever, and we could use that to access, and then you could have multiple images per class. But this is just the way I kind of built it quickly and dirtily this morning. But yeah, so you basically feed in your model, you feed in your device string, whether you're targeting CPU or CUDA, and then target is going to be like hen, Samoyed, clog, etc., or whichever one of these images that you want. And it's just going to classify how well the model did on classifying that image. This model folder, this is just where our ResNet model lives, nothing particularly new. If you've seen any of my coding tutorials, you'll be familiar with this. Then I have a utils section where I basically just cleaned up the main script. So in my last advanced graph mode manipulation video, we did a lot of this, graph traversal, and also this kind of manipulation where we fused in batch norms into preceding comps. And we will actually be using this function, but generally I just hid this away, so it's not in the main script and it's kind of hidden away. This is the IPBD system exception hook, which still might be the favorite piece of code I've ever found on the internet ever. It's just beautiful. It's just, if you fall into any sort of exception, it'll throw you into an IPBD breakpoint, which I love very much. And then these are our qconfigs. And qconfigs, in case you don't know, they're basically the recipe on how we're going to quantize a specific layer. For example, if a layer was quantized with this specific qconfig, it would do learnable fake quantize, and learnable fake quantize is going to be super relevant for QAT because there's different quantization modules that are available. There's learnable fake quantize, there's fake quantize, there's fixed qparams fake quantize, and the differences between those 3 all come down to how one can update the quantization parameters. So in the case of fixed qparams fake quantize, the quantization parameters cannot change. They can't be updated via observation PTQ or classic PTQ. They can't be updated via QAT. They're just fixed. They live there forever. They don't change. Fake quantize can only be updated via PTQ observation, i.e. what I'm calling classic PTQ, and then learnable fake quantize can be updated via classic PTQ and via QAT. And so the difference between these and these is that I'll actually show the code. So if we go to here, so this is the Torch AO quantization library, which you should get very familiar with if you're dealing with PyTorch quantization. This is where most of the code lives. This is the learnable fake quantization module, and we can see that the scale and the 0 point are stored as model parameters, and because they're parameters, that means they take gradients. But if we go to fake quantize, which is where the fake quantization module lives, we can see something. Yeah, we can see that the scale and the 0 point, they're not treated as model parameters, they're treated as buffers. And the only real difference between buffers and parameters, as far as I know, is that parameters can take gradients and buffers cannot. These can still be updated via observation, like, the observer will go through the process of updating the data in these buffers, but these won't take gradients. So that's really the fundamental difference between learnable fake quantize and fake quantize. But yeah, back to the code. So I said that these were learnable fake quantize. That just means that the quantization parameters can take gradients. For weights, we're also going to be doing learnable fake quantize, but here our observer is per channel minimax observer. And then we have this fake quant activation. I don't think we actually use this in the case of this example. But yeah, that's basically everything you need to know about that. This is all code that we've seen before. So here we initialize our model, we add our IPBD breakpoints, we define the qconfigs, we assign the qconfigs, we do the quantization and symbolic tracing. That all happens in prepare QATFX. It does a symbolic trace of the model and then it does the quantization. So this is not just a quantized model, but it's also a FX graph traced model. We evaluate our models. As we can see now, we have to feed in the Samoyed keyword or clog or hen or whatever when we're evaluating. Previously, we didn't have to do that. We print the graph as a table. We do this fusing of batch norms into convs, just because that's something I prefer to do for the sake of this. So when we're doing QAT, we're no longer going to have batch norm layers in our model. We're just going to have convs and relus, essentially. And that is it. And so we're going to be mainly working off of this transformed model, this one. So that's what we're going to be doing. And then now we can get into the meat of the video, which is quantization aware training. So to do this, because we are doing a training loop, we're going to need a certain amount of things. We're going to need an optimizer. We're using Adam today. We're going to use some sort of loss. Today we're using cross entropy loss because ResNet does image classification, so that's appropriate. This is just kind of some typing stuff. Transforms as well is going to be useful, and then path is just the path lib thing because we have a lot of paths in our directory. We initialize our optimizer. I used a really small learning rate. I tried a learning rate of 1 to the e minus 3, but that actually ended up massively overfitting, so that was a bit of an issue. But 1e minus 5, it doesn't massively overfit, but we will see the dangers of overfit today, so this video doubles up doing two things. We do QAT, but we also discover how easy it is to overfit stuff. This is our loss function. To basically, as we're doing our training loop, and I'll come back to these functions in a little bit, but first we're just going to do a random, completely arbitrary number of epochs, and we take our batched images. It was a hen and a Samoyed. So this function, it'll go into these images, it'll take the hen and it'll take the Samoyed and it'll do some image processing. So it'll center crop, it'll normalize the tensors, and then it's going to batch them together. So these are all going to be included in the same batch. So there's going to be one picture of a hen, there's going to be another picture of a dog in the same batch. And then this is going to do the same thing, except it's only going to work on the labels. So it's going to search through the ImageNet classes for hen, for example, or Samoyed, and then it's going to return this value, -1 because of 0 indexing. And then it's going to create a one-hot vector for that class, and then that is also going to get batched. So at the end, this is going to output 2 images that have been batched together after some processing, and then the associated one-hot vectors. We're just going to use that as our training data. If you were very serious about training this ResNet model, you should download the ImageNet data and you can use that in a data loader. But I've just built this, and you can see an example of kind of how you would build a very rudimentary training loop from scratch. You know, when things aren't abstracted away, what it actually looks like. But at the end of the day, fine, we feed in that batch of a hen and a dog. We get our predictions. Our predictions are going to be non-normalized, so we're going to apply a softmax operation, so we're going to get probabilities. And I think this is probably a good place to enter our breakpoint, so to speak. And then also we do a couple extra things here, which is we're printing the scale and the 0 point for a given layer. So here we're just taking activation post-process 0 for our transformed model, and we're just going to print, what the scale and 0 point are before QAT, and we're going to print them what they look like after QAT. And then here, in case you haven't seen this before, we calculate our loss, we clear our optimizer, we backpropagate the loss, and then we step with our optimizer. And our optimizer is going to take the gradients that have been backpropagated in this line, it's going to read them, and then according to the Adam optimizer, according to the learning rate, it's going to update the model parameters based on how Adam does so. And then here we're also just printing the mean loss for every log frequency, which is 10. So every 10 iterations, it's going to print the average loss that we've had so far. But I am just going to run this. And we're going to get thrown into a breakpoint here where there's this error. So if we look at probabilities, and I guess if we look at size, okay, so yeah, we can see that there's 2 instances in this batch, and there's 1,000 different values. Each one of these is the probability associated with one of the classes. So there are 1,000 ImageNet classes. Go all the way to the bottom. Wow, of course, toilet tissue is the last one. But yeah, there's 1,000, so it outputs a probability for each one of those, and then because there's 2 instances in our batch, a hen and a Samiad. But let's look at what the maximum is. So if I look at Torch, I guess max probabilities, dimension 1. Okay, we can see that 8 and 258, so is that correct? If I go to Samiad, okay, 259, I think with one-off indexing, because this list starts at 1 and this starts at 0, I think that is correct, which I would be shocked if it wasn't, frankly. And then I'm also going to search for hen. Hen is 8, which is 9 with 0 indexing as well, so that is perfectly fine. So it is putting the probabilities that we would expect so far, which is cool because it's a quantized model, but it's still doing well. So that's kind of nice to see. But then we're going to do a little bit of QAT just because we're going to say, you know what, this doesn't quantize well enough. We want this to quantize even better. We're going to train this a little bit more. And in this case, we are very much overfitting to this image of a hen and this image of a Samiad. You should not do this unless you are like desperate to only classify hens and Samiads really well and you don't care about classifying anything else. And specifically if you really want to classify these specific images really well, because there's no guarantee that this is going to generalize to other images of hens and Samiads. Like this is not responsible machine learning. I'm just kind of showing how this would work in code. But generally speaking, you should have a much broader training set. But yeah, anyway, probably not telling you anything you don't already know. And now we're gonna look, what am I looking at? Where is it? Why am I, oh, batch labels, sorry. That took me way too long to figure out. Torch max. And then, because these are one-hot vectors, this is going to come up as the same. So yeah, 8, 2, 5, 8. This just tells us that everything else is basically 0. So if we looked at these one-hot vectors, yeah, they're just zeros everywhere and they're ones wherever the ground truth is. So there'll be a 1 at 8 for this vector and there'll be a 1 at index 258 for this vector. And that's why the cross entropy is going to work, because the cross entropy is trying to minimize the difference between this probability distribution and whatever is outputted by the softmax. But yeah, anyway, that's basically most of it covered, and we can see that the loss is kind of going down, barely. But like, we shouldn't expect too much from this. The learning rate's very small. There's only 2 training examples. So yeah, we're basically overfitting this model. So, proceed with caution. Okay. So yeah, we transformed it and it classified a Samiad at 0.876 probability. Now, after fine-tuning on the picture of the Samiad and a picture of a hen, it's almost 100% probability that it is a Samiad based on this exact same picture. And I guess we can also look at this, that we can see that the quantization parameters have updated a little bit. So it was 128. Okay, it was still 128 before. Now the scale parameter is 0.022 instead of 0.298. But yeah, mostly we can see that, like, wow, it's now doing a really good job on classifying a Samiad. It's doing a really good job on classifying a hen. It's also doing this. I noticed before when I was putting this example together. It also does a really good job, even though it's been completely overfitted to pictures of Samoyeds and hens. It also classifies as clogs really well. I take that just because this could not possibly be anything else. Like if you look at it's not an ostrich. Oops. Yeah. It's not a bald eagle. It's not a ringneck snake. It's not a black widow. It's not a Norfolk Terrier. Like literally, pretty much the only thing in this entire list of things that it could be is a clog. So I'm not reading too much into the fact that this just classified clogs really well. I think it speaks more to the quality of the image than it does to the fact that we didn't overfit our model. It also says it could be a shoe shop or a sandal, cowboy hat, boot, but yeah, it's very confident in it being a clog, which, fair enough, because again, it's very much a clog. But then if we look at mailbox, we can see that, okay, now it's not doing that good of a job anymore. So it could be parallel bars, it could be a solar dish, it could be a cannon. It does guess that in the top 5 guesses of what it could be, it does correctly guess mailbox, but it also guesses pole. And actually, I haven't actually done this yet, but I'm going to test how does the floating point model do on this, because we still have access to that. So if I go, I think it's just original model, it's called. I'll be curious to see. Okay, so even the original model, it struggles to classify that as a mailbox. It still thinks it could be a solar dish. Okay, yeah, like the QAT model thinks it's more likely to be parallel bars. This one thinks it's more likely to be solar dish, but they're very close. I mostly think that that's going to be because this is a very blurry image. Just even the floating point model is struggling to classify this, so fair enough, so is the QAT model. So I've actually kind of failed in my attempt to scare you about overfitting, that we've kind of overfitted to a picture of a hen and a Samoyed. So actually we're going to get a bit more aggressive about this, and we're going to, jump into the future for when this training loop is finished. So I will see you then. Okay, so the model finished training, and yeah, fine, it's classifying a Samoyed well, it's classifying a hen well, it's classifying a clog well, so it hasn't yet overfitted to Samoyed and hen, but somehow it's classifying mailbox better than it was earlier, which makes zero sense. Somehow by overfitting to a hen and a Samoyed individual pictures, somehow we're classifying the mailbox better than we were before. Let me actually check this, evaluate the floating point model mailbox. Yeah, somehow the quantized overfitted model is somehow classifying a mailbox better than the original one. You know what? We're gonna increase the learning rate. This should do it. And we're gonna I don't think we're gonna need 500 iterations for this. I'll go back to 50. Alright, take 2. Alright, here we go. Yeah, 50 iterations and a larger learning rate. So we can see that we're perfectly classifying a Samoyed to the point that it's actually a problem, and we're actually failing to classify the hen. It's just saying everything is a Samoyed, everything is a Samoyed, everything is a Samoyed. I don't know why it chose to more accurately, overfit to Samoyed instead of overfitting to hen. For whatever reason, deep learning magic. That is what it is. But anyway, yeah, all this to say that this is how you do a QAT training loop. And generally this is how you might do a training loop if you don't have a data loader available, or you need to make your own custom data set for whatever reason. You can see that QAT is nothing special, it's just a training loop. And if we go into transformed, and we can look at activation post-process 0, we can look at any arbitrary layer of them, and we look at if fake quant enabled, that is true. And I think it is, yeah, I mean, we can literally just check the scale. It requires grad, so it is learning, and then the same with the 0 point. We can see that these are taking gradients and they're learning. So yeah, that is it for the tutorial. There's not much that more to cover in QAT. I'll probably have a video in the future talking more about the theory, about learn step size quantizer, about different kinds of QAT, but this is really the basics. And it's actually super easy. So if you have a model and you have training data, then QAT is going to be as simple as assigning qconfigs that have learnable qparams. So if we go here, these have learnable qparams just by using the learnable fake quantized class, and then using a training loop, adding those to the optimizer. Make sure you do add those to the optimizer. Sometimes people make the mistake that they don't, and then the optimizer doesn't see the quantization parameters, it can't update them. and things don't really work out very well. So yeah, just be sure you add that. But other than that, it's fairly simple. I hope this was useful. I hope this was informative. And yeah. Alright guys, that was it on the QAT video. We didn't do anything crazy. We just created a custom sort of data loader that really was overfitting quite heavily to 2 images that we batched together and we fed it. But it works for just the example of showing how QAT works. And yeah, then we did a little training loop and that was it. So yeah, QAT is quite simple. Nothing all that complicated to do it. I do generally recommend it. It can, obviously the problem with training is that then you have to train the model and that can be kind of expensive. So there's a lot of post-training quantization techniques available and I'll have videos on those. But I will say that I'm very excited because understanding this little bit about QAT and that, okay, the gradients go backwards and yada yada, that might be useful for a next video that I'm going to make, which is this visualization tool that I've wanted to build forever, and I finally had some free time and I built it and it works and I'm super excited about it. So I'm going to be sharing that in the next video. Stay tuned for that. I think that's a very useful tool for kind of debugging why maybe your quantization isn't working as well as it could. But yeah, that'll be the next video. If you have any videos that you would like to see, please just send me a message, leave a comment, whatever. And yeah, like and subscribe. I hope you have a nice day wherever you are, and see you in the next one. Bye.